Imagine standing before a world map and suggesting that the continents were once joined together as a single enormous landmass. Imagine claiming that Africa and South America were not always separated by the Atlantic Ocean, that Europe and North America had once been connected, and that the mountains, fossils, and rocks found on opposite sides of oceans were pieces of the same ancient landscape. Today, these ideas are taught in classrooms around the world. But when they were first proposed, they were considered so extraordinary that many scientists dismissed them outright. The man behind this revolutionary idea was Alfred Wegener. He was not trying to start a scientific revolution. He was simply trying to explain observations that did not fit the accepted understanding of the Earth. By following evidence wherever it led, he challenged one of the deepest assumptions in geology and laid the foundation for one of the most important theories in modern Earth science. Ironically, he would spend much of his life defending an idea that the scientific community largely rejected during his lifetime. Only years after his death would the world fully recognize how profoundly he had changed our understanding of the planet. Alfred Lothar Wegener was born in Berlin, Germany, in 1880. From an early age, he showed a fascination with the natural world. Unlike many children who focused on a single subject, Wegener developed broad scientific interests. He was drawn to astronomy, physics, meteorology, geography, and the complex systems that govern the Earth. This wide-ranging curiosity would later become one of his greatest strengths. Rather than viewing scientific disciplines as separate, Wegener believed that different fields could help explain one another. He looked for connections where others saw boundaries. He studied physics, astronomy, and meteorology at universities in Berlin, Heidelberg, and Innsbruck. His formal education gave him a strong mathematical and scientific foundation, but his greatest passion became the Earth's atmosphere. At the beginning of the 20th century, meteorology was still developing into a modern science. Weather forecasting was limited, atmospheric processes were poorly understood, and researchers were eager to gather new observations. Wegener embraced this challenge. He became an expert in atmospheric science and participated in balloon experiments that pushed the limits of human endurance. Together with his brother Kurt, he undertook long-duration balloon flights to study atmospheric conditions at high altitudes. These are not ordinary journeys. The balloons carry them far above the ground for extended periods, exposing them to freezing temperatures, unpredictable winds, and considerable danger. In one record-setting flight, the brothers remained airborne for more than 52 hours, an extraordinary achievement for the time. These experiences taught Wegener something that would shape his scientific thinking. Nature could only be understood through careful observation. Theories were valuable, but they had to be tested against real evidence gathered from the world itself. His growing reputation as a meteorologist opened opportunities to join expeditions to Greenland. At the time, Greenland represented one of the least explored environments on Earth. Vast ice sheets covered much of the island, creating an ideal natural laboratory for studying glaciers, climate, weather, and polar conditions. For Wegener, these expeditions were irresistible. Beginning in 1906, he traveled to Greenland, where he spent months conducting scientific observations under some of the harshest conditions imaginable. Life on the ice demanded extraordinary endurance. Temperatures plunged far below freezing. Powerful winds swept across the frozen landscape. Supplies were limited. Communication with the outside world was often impossible. Yet Wegener thrived in these environments. He carefully recorded weather patterns, measured atmospheric conditions, and studied the movement of ice across the landscape. His experiences deepened his appreciation for the immense forces shaping the Earth's surface over long periods of time. The Arctic also taught him patience. Natural processes often unfolded slowly, almost imperceptibly. Glaciers advanced only small distances each year, yet over thousands of years they transformed entire continents. Small movements, given enough time, could reshape the world. This idea would later become central to his most famous theory. While continuing his work in meteorology, Wegener also developed an increasing interest in geology. He began reading scientific papers describing fossils found on different continents. Some discoveries puzzled him. Identical fossil species appeared in places now separated by vast oceans. Certain rock formations on opposite sides of the Atlantic looked remarkably similar. Mountain ranges seemed to align if the continents were placed together. Each observation by itself might have seemed unremarkable. Together, they formed a pattern. One day, while examining a world map, Wegener noticed something that many people had casually observed before, but few had taken seriously. The coastlines of South America and Africa appeared to fit together almost like pieces of a giant puzzle. This alone was not proof. Coastlines change over time through erosion and rising sea levels. But combined with the fossil evidence, matching rock formations, and similarities between ancient mountain systems, the resemblance became difficult to ignore. The more evidence Wegener gathered, the more convinced he became that the continents had once formed a single supercontinent before slowly drifting apart over immense spans of geological time. This idea directly challenged the prevailing view. Most geologists believed that continents and oceans had always occupied roughly their present positions. The Earth's surface was considered relatively fixed. Wegener proposed something radically different. He argued that continents were not permanent. They moved, slowly, relentlessly, across the face of the Earth. It was a breathtakingly bold idea. But proposing a revolutionary theory was only the beginning. Convincing the scientific world would prove to be a far greater challenge than discovering the idea itself. In 1912, Alfred Wegener formally presented one of the most controversial ideas in the history of Earth science. He proposed that the continents had once been joined together in a single enormous landmass and had gradually drifted apart over millions of years. To many people today, this sounds like an ordinary scientific fact. But at the beginning of the 20th century, it challenged nearly everything geologists believed about the Earth. The reaction was immediate. Some scientists were intrigued. Many others were skeptical. A large number dismissed the idea altogether. Wegener understood that a claim of this magnitude could not rest on intuition alone. If he wanted the scientific community to take continental drift seriously, he needed evidence from as many different fields as possible. Fortunately, his broad scientific background allowed him to think differently from many specialists. Rather than focusing only on geology, he drew information from paleontology, climatology, geography, geophysics, and biology. He believed that if multiple branches of science pointed toward the same conclusion, the overall case would become much stronger. His first line of evidence came from fossils. One of the most striking examples involved a freshwater reptile called Mesosaurus. Fossils of this ancient animal had been discovered in both southern Africa and eastern South America. This presented a problem. Mesosaurus lived in freshwater lakes and rivers. It could not have crossed the vast Atlantic Ocean. If the continents had always been separated by thousands of kilometers of ocean, how had identical fossils appeared on both sides? The simplest explanation, Wegener argued, was that the continents had once been connected. He found similar patterns elsewhere. The fossil plant Glossopteris appeared across South America, Africa, India, Antarctica, and Australia. These regions are now separated by enormous oceans, yet they contained remarkably similar fossil evidence. Again, the distribution made much more sense if the continents had once formed a single landmass. The fossil record was only the beginning. Wegener also studied mountain ranges. He noticed that geological formations on opposite sides of the Atlantic appeared to continue from one continent to another. The Appalachian Mountains in eastern North America matched mountain belts found in Scotland and Scandinavia when the continents were reconstructed into their earlier positions. It was as though a single mountain chain had been split apart. Rock formations told the same story. Scientists found layers of rock with similar ages, compositions, and structures on continents now separated by oceans. These similarities were too consistent to ignore. Then there was the evidence from ancient climates. This was perhaps one of Wegener's most compelling arguments. geologists had discovered signs of ancient glaciers in regions that today lie near the equator, including parts of Africa, India, South America, and Australia. These areas now experience warm or tropical climates. Why would glaciers have existed there? Conversely, coal deposits, which form from lush vegetation growing in warm, swampy environments, were found in places that are now cold northern regions. The ancient climates did not match the present locations of the continents. Wegener proposed a remarkably simple explanation. The climates had not changed dramatically because the continents had remained fixed. Instead, the continents themselves had moved through different climate zones over immense spans of time. When viewed together, the evidence formed a coherent picture. Matching fossils, matching mountain ranges, matching rock formations, ancient climate patterns. The puzzle pieces all pointed toward the same conclusion. Long ago, Earth's continents had been united. Wegener gave this ancient supercontinent a name, Pangaea. Derived from Greek words meaning all Earth, Pangaea represented a single gigantic landmass surrounded by a vast global ocean. According to Wegener, this supercontinent gradually broke apart over millions of years, with its fragments slowly drifting into their present positions. Today, images of Pangaea appear in textbooks around the world. But when Wegener introduced the concept, it seemed almost unbelievable. His critics acknowledged that some of the evidence was interesting. What they could not accept was his explanation. The central question remained unanswered. What force could possibly move entire continents? This was the greatest weakness in Wegener's theory. He knew the continents had moved, but he could not convincingly explain how. Wegener suggested that forces related to Earth's rotation and tidal interactions might slowly push continents across the planet's surface. Unfortunately, these proposed mechanisms were incorrect. Physicists quickly demonstrated that such forces were far too weak to move entire continents. For many geologists, this flaw overshadowed all of the supporting evidence. If the mechanism was wrong, they argued, then perhaps the theory itself was wrong. Some critics became openly hostile. Scientific journals published harsh reviews. Conferences featured intense debates. Many respected geologists dismissed continental drift as speculation rather than science. Some even ridiculed the idea. To them, continents were simply too large and too solid to move. The Earth's crust appeared permanent and immovable. Wegener, however, remained remarkably calm. He did not respond with anger or personal attacks. Instead, he continued collecting evidence. He revised his arguments, published new editions of his book The Origin of Continents and Oceans, and carefully addressed criticisms wherever possible. Each edition contained more data than the last. He believed that if enough observations pointed in the same direction, the truth would eventually become impossible to ignore. This determination reflected his character. Wegener was not driven by a desire to win arguments. He was driven by a desire to understand the Earth. He knew that every major scientific breakthrough faces resistance when it challenges deeply established beliefs. History had shown this repeatedly. New ideas often appear impossible until the evidence becomes overwhelming. Still, the opposition took its toll. Many leading geologists refused to accept continental drift for the remainder of Wegener's life. His theory remained on the margins of mainstream geology despite the growing body of evidence supporting it. Yet beyond the debates and criticism, Alfred Wegener continued doing what he loved most. He returned again and again to Greenland. The frozen island had become more than a research destination. It had become part of his life's work. There, surrounded by glaciers, snowfields, and some of the harshest conditions on Earth, he continued studying the natural forces that slowly reshaped the planet. He could not know it then, but it would be during one of these expeditions that both his greatest personal challenge and the final chapter of his life would unfold. By the late 1920s, Alfred Wegener had become one of the most debated scientists in the world. His theory of continental drift continued to attract attention, but not the kind most researchers hoped for. While a small number of scientists found his evidence persuasive, Many of the leading geologists of Europe and North America remained unconvinced. The criticism was often relentless. Some scientists acknowledged that the continents appeared to fit together remarkably well. Others admitted that the fossil evidence was difficult to explain using traditional theories. But almost all of them returned to the same objection. What force could move entire continents? Without a convincing physical mechanism, many believed Wegener's theory could not be accepted. This frustrated him deeply, though not because of wounded pride. He understood that science demanded explanations, not simply observations. He also recognized that his proposed mechanisms involving Earth's rotation and tidal forces were incomplete. But he believed that the weakness of one part of the theory should not erase the strength of the evidence supporting the rest. Again and again, he reminded colleagues that scientific history contained many examples where observations were accepted before the underlying mechanism was fully understood. The planets had been observed moving around the sun before gravity itself was explained. Electricity had been studied long before scientists understood the behavior of electrons. Nature often revealed facts first. Explanations came later. Unfortunately for Wegener, many of his contemporaries were unwilling to separate those two stages. Despite the controversy, he refused to abandon his research. Instead, he continued expanding his work in meteorology and polar science. Greenland remained at the center of his scientific life. Few places on Earth fascinated him more than the vast island covered by one of the planet's largest ice sheets. Greenland was an unforgiving environment. Winter temperatures could fall below minus 50 degrees Celsius. Blizzards could continue for days. Powerful winds swept across the ice with little warning. Travel required extraordinary planning, physical endurance, and complete trust among expedition members. Yet Wegener returned repeatedly. He believed the Greenland ice sheet held valuable information about climate, weather patterns, and the long-term behavior of Earth's atmosphere. Understanding these systems required direct observation under the harshest possible conditions. Unlike many scientists who remained primarily in laboratories, Wegener combined theoretical thinking with field exploration. He was willing to endure enormous personal risk in pursuit of knowledge. His expeditions demanded months of preparation. Supplies had to be transported across hundreds of kilometers of ice. Food, fuel, scientific instruments, and survival equipment all had to be carefully managed. A single mistake could place the entire expedition in danger. In 1930, Wegener organized what would become his most ambitious Greenland expedition. Its goal was to establish and maintain scientific observation stations deep within the ice sheet, gathering valuable meteorological data throughout the harsh Arctic winter. The project was extremely challenging. Researchers stationed in the interior depended entirely on supply teams crossing dangerous stretches of ice before winter weather made travel nearly impossible. As conditions worsened, serious logistical problems developed. Snowstorms delayed transport. Temperatures dropped rapidly. Food and fuel became increasingly difficult to deliver. Some members of the expedition were isolated far from the coast. Wegener realized that waiting could place lives at risk. Although he was already 50 years old and physically exhausted from months of difficult work, he decided to personally lead a rescue and supply mission across the Greenland ice sheet. Many would have delegated the task. Wegener chose to go himself. Accompanied by a small team, he set out across one of the most hostile environments on Earth. The journey required pulling heavy sledges through deep snow while enduring relentless winds and freezing temperatures. Every kilometer demanded immense physical effort. Breathing became painful in the icy air. Progress was slow. Visibility often disappeared during storms. Still, the team pressed forward. After tremendous effort, they reached the isolated research station and successfully delivered desperately needed supplies. The mission itself was a success. The scientists stationed there now had a chance to survive the Arctic winter. But Wegener had pushed himself to the limit. The journey had drained nearly all of his strength. On the return trip, conditions remained brutal. The cold intensified. Fatigue accumulated. Each step became more difficult than the last. Then, sometime in early November 1930, Alfred Wegener died on the Greenland ice sheet. He was 50 years old. The exact cause was never established with complete certainty, but exhaustion combined with the extreme Arctic environment almost certainly played a decisive role. His companions later buried him beneath the snow, marking the location as best they could. Months later, when search teams returned after winter, they recovered his body. He was found peacefully lying inside his sleeping bag, as though he had simply fallen asleep after completing one final act of service for his colleagues. His grave remained in Greenland, the landscape he had studied and loved for so many years. The news of his death spread through the scientific world. Many mourned the loss of a dedicated explorer and meteorologist. Few realized that one of the greatest revolutions in geology had lost its strongest advocate. At the time of his death, continental drift was still rejected by most geologists. His evidence remained controversial. His central idea remained outside the scientific mainstream. To many observers, Alfred Wegener appeared to have died defending a theory that history would eventually forget. But history had not finished with his ideas. Far beneath the oceans, hidden from every scientist of his generation, lay the evidence that would one day prove he had been astonishingly close to the truth. The Earth itself was quietly preserving the answer. It simply had to wait for technology advanced enough to reveal it. When Alfred Wegener died on the Greenland ice sheet in 1930, it seemed as though his greatest scientific idea might disappear with him. Continental drift remained one of the most controversial theories in geology. Most textbooks continue to describe the continents as essentially fixed, and many of the world's leading geologists regarded Wegener's work as an interesting but ultimately flawed hypothesis. For nearly 2 decades after his death, very little changed. The Second World War soon redirected the attention of scientists toward military technology, engineering, and national defense. Yet, in an unexpected way, the war would also create the tools that eventually transformed geology forever. During and after the war, governments invested heavily in technologies capable of exploring the oceans. Sonar systems were developed to detect submarines, allowing researchers to map the seafloor with a level of detail that had never been possible before. What scientists discovered beneath the oceans was astonishing. The ocean floor was not flat. Stretching across the globe were enormous underwater mountain ranges thousands of kilometers long. These formations, known as mid-ocean ridges, formed a continuous network unlike anything previously imagined. Even more surprising were the deep ocean trenches found elsewhere across the planet. The seafloor itself appeared to be active. It was not the ancient, unchanging surface that many geologists had assumed. As researchers continued studying these underwater landscapes throughout the 1950s and early 1960s, another remarkable pattern emerged. The rocks nearest the mid-ocean ridges were relatively young. Farther away, the rocks became progressively older. This suggested that new oceanic crust was constantly being created along the ridges before slowly moving outward in both directions. The idea became known as seafloor spreading. For the first time, scientists had identified a mechanism capable of moving enormous sections of Earth's surface. The missing piece of Wegener's theory was beginning to appear. Further evidence arrived from an unexpected source. Earth's magnetic field has reversed many times throughout geological history. When molten rock cools, tiny magnetic minerals inside it align with the direction of the planet's magnetic field at that moment. As scientists measured magnetism across the ocean floor, they discovered symmetrical bands of magnetic patterns on either side of the mid-ocean ridges. These magnetic stripes formed a perfect geological record. They showed that new crust had repeatedly formed at the ridges and gradually moved away over millions of years. The evidence was overwhelming. The seafloor itself was moving. If the ocean floor moved, then the continents resting upon Earth's outer shell could move as well. Wegener had been right about continental motion. He had simply lacked the technology needed to explain how it happened. During the 1960s, geologists developed a new theory that united Wegener's observations with these discoveries. It became known as plate tectonics. According to this theory, Earth's outer shell is broken into massive rigid plates that slowly move across the softer mantle beneath them. These plates carry both continents and ocean floors together as a single system. Where plates move apart, new crust forms. Where plates collide, mountains rise. Where one plate sinks beneath another, earthquakes and volcanoes occur. Suddenly, dozens of geological mysteries found a common explanation. The formation of mountain ranges, the distribution of earthquakes, the chains of volcanoes surrounding the Pacific Ocean, the opening and closing of oceans, the movement of continents. All of these processes became part of one unified picture. Plate tectonics quickly became the central organizing theory of modern geology. Many scientists have compared its importance to Darwin's theory of evolution in biology. It fundamentally changed how humanity understands the Earth. And at the heart of that revolution stood Alfred Wegener. His original theory had not been entirely correct. He misunderstood the mechanism responsible for continental movement. The continents were not plowing independently through the ocean floor, as he had imagined. Instead, both continents and oceans moved together on enormous tectonic plates. But the central insight that continents had once formed a single supercontinent and later drifted apart was remarkably accurate. Considering the limited evidence and technology available in the early 20th century, Wegener's achievement was extraordinary. He had assembled clues from fossils, rocks, mountain ranges, and ancient climates into a coherent explanation that anticipated one of science's greatest breakthroughs by several decades. The scientific community gradually acknowledged this remarkable accomplishment. Geologists who had once dismissed continental drift now recognized Wegener as one of the pioneers whose vision made plate tectonics possible. His books, once heavily criticized, became historical landmarks in earth science. Students studying geology learned not only the modern theory, but also the story of the scientist who first dared to imagine moving continents. His influence extended beyond geology. Wegener demonstrated the power of interdisciplinary thinking. He was trained as a meteorologist, yet he transformed geology. He combined evidence from multiple scientific fields rather than remaining confined within a single discipline. This approach has become increasingly important in modern science, where many of the greatest discoveries occur at the boundaries between traditional subjects. Alfred Wegener never lived to witness the acceptance of his greatest idea. He never saw plate tectonics become one of the most successful scientific theories ever developed. He never heard classrooms around the world teaching concepts that had once brought him criticism and ridicule. But history has a way of rewarding those who follow evidence with courage, even when recognition arrives far too late for them to see it. Today, more than a century after Alfred Wegener first introduced the idea of continental drift, it is difficult to imagine Earth science without his influence. Every modern map showing tectonic plates, every explanation of earthquakes and volcanoes, every reconstruction of ancient supercontinents, and every geological model describing the movement of the Earth's surface traces part of its intellectual history back to the questions he dared to ask. His vision permanently changed how humanity sees the planet. Before Wegener, continents were often viewed as fixed features, almost permanent fixtures of the Earth's landscape. Mountains rose, rivers changed course, and coastlines slowly eroded, but the continents themselves were believed to have occupied roughly the same positions for hundreds of millions of years. After Wegener, and especially after the development of plate tectonics, the Earth became something entirely different, a living planet, not alive in the biological sense, but constantly changing, constantly reshaping itself through forces operating deep beneath its surface. The continents are not motionless. Even now, at this very moment, they continue to move. Africa is slowly pushing toward Europe. Australia is drifting steadily northward. The Atlantic Ocean continues to widen as new crust forms along the mid-Atlantic ridge. The Pacific Ocean is gradually shrinking as tectonic plates descend into deep ocean trenches. These movements are incredibly slow, usually measured in only a few centimeters each year. Yet over millions of years, they reshape the face of the Earth. Entire oceans open and close. Mountain ranges rise. Ancient continents break apart. New supercontinents eventually begin to form. The planet that appears stable within a human lifetime is, on a geological timescale, in constant motion. Wegener was among the first scientists to truly understand this profound reality. His work also transformed many other branches of science. Paleontology gained a clearer explanation for the distribution of ancient fossils across distant continents. Biologists better understood how species evolved after populations became separated by drifting land masses. Climatologists reconstructed ancient environments by tracing the movement of continents through different climate zones. Geophysicists developed increasingly sophisticated models of Earth's interior to explain the forces driving plate motion. Even the search for natural resources changed. Modern exploration for oil, natural gas, minerals, and groundwater frequently relies on plate tectonic theory to understand how geological structures formed over immense spans of time. Natural hazard research also depends heavily on Wegener's legacy. By understanding plate boundaries, scientists can better identify regions vulnerable to earthquakes, volcanic eruptions, and tsunamis. Although precise prediction remains impossible, the theory has greatly improved humanity's ability to assess geological risks and prepare for natural disasters. Perhaps the most remarkable aspect of Wegener's story is not simply that he proposed a revolutionary idea, is that he trusted evidence even when nearly everyone around him disagreed. Scientific progress often requires exactly this kind of courage. Not stubbornness, not blind confidence, but the willingness to follow observations wherever they lead, even if they challenge deeply accepted beliefs. Wegener never claimed to possess every answer. In fact, he openly acknowledged that he could not fully explain the force responsible for continental movement. Many critics focused on this weakness. History, however, revealed an important lesson. A scientific theory can contain an incomplete explanation while still identifying a fundamentally correct truth. Later generations, equipped with better technology and new discoveries, completed the picture that Wegener had begun. This is how science often advances. Each generation builds upon the questions left unanswered by the previous one. No discovery stands entirely alone. Every breakthrough becomes part of a much larger human conversation stretching across centuries. Alfred Wegener's contribution reminds us that imagination has an essential place in science. Without imagination, no one would ask new questions. Without evidence, imagination becomes speculation. Wegener combined both. He imagined that the continents had once been united, but he also spent years collecting fossils, rocks, climate records, and geological observations to support that vision. His conclusions were bold because his evidence demanded bold thinking. In recognition of his extraordinary contributions, research institutes, scientific awards, mountains, glaciers, and even a crater on the moon now bear his name. His books remain milestones in the history of geology, not because every detail proved correct, but because they changed the direction of scientific thought. He is remembered not merely as the father of continental drift, but as one of the pioneers whose work laid the foundation for the modern theory of plate tectonics. Perhaps the greatest tribute to Alfred Wegener is that his revolutionary idea is no longer considered revolutionary at all. It has become part of humanity's basic understanding of the world. Students learn it in classrooms. Scientists rely on it every day. Explorers, engineers, and researchers use it to interpret landscapes across the globe. The continents continue their silent journey, just as they did millions of years before Wegener was born, and just as they will millions of years after us. Their movement is almost invisible within a single lifetime. But Alfred Wegener taught humanity something extraordinary. The greatest changes on Earth often happen so slowly that they cannot be seen by one generation alone. They reveal themselves only to those willing to look beyond the limits of a single lifetime and imagine the planet as it truly is, a world forever in motion.